How about we actually start the next exciting session here? So I think I'd like to introduce two great speakers coming from GumGum company. Nishita Sant, and she's the manager for the computer vision group there. And also Greg Chu, which is a senior computer vision scientist. So I think just a few words about them, So I think we all have seen, based on neural networks, there is a lot of models that we create regarding the object detection or image classification. So I think Nishita is actually bringing some nice insight into this particular area by her experience, not only in the building the computer models, but also in deploying from an infrastructure perspective, and also her wide experience, not just in imaging, but also in the medical area as well. So that brings a good dimension to this particular presentation. And also Greg, I think he is PhD in this space, and then he has done a lot of tumor segmentation as well from a medical side. So I think they both are going to talk about not just the edge, because most of the sessions we had this morning in this particular track, they're focused on the edge side. I think now we are going to move a little bit more on the cloud side. So how do we build this flexible and scalable infrastructure, AI-based platforms on the cloud? So please welcome GumGum team.
Hi, I'm Nishita, and I'm an engineering manager for the computer vision team.
Hi, I'm Greg. I'm a senior computer vision scientist.
And today we're going to be talking about creating efficient, flexible, and scalable vision solutions in the cloud. Before we start, here's a little overview of what we do at GumGum. We invented in-image advertising, in which we contextually place ads in line with content that our clients are actively and continuously engaged with. The tool on the right here is called the Media Value Center, through which we help marketers as well as rights holders capture the value of their sponsorship through social media, broadcast, as well as streaming. And if anybody of you would like to know more, we'd be more than happy to talk offline. So today we'll start with motivating computer vision solutions in the cloud, and then we'll deep dive into computer vision system design through principles that we consider important at GumGum. And towards the end, we'll put it all together through a relevant example and wrap it up with key takeaways. So we've been talking about computer vision solutions at the edge versus at the cloud, and by now all of us know for sure that this decision is not binary. It really depends on a number of factors. Let's talk about hardware reliability. Unlike at the edge, it is your cloud service provider's responsibility to provide continually reliable hardware. Now, latency is definitely a concern in the cloud, but if your application is not going to be critically affected by minor outages, I think the cloud is your best bet, specifically because of the availability of a plethora of hardware and software resources, not having to worry as much about power, size, and cost constraints. And in my opinion, one of the biggest advantages of using the cloud is the ability to serve high volume data. So let's say we've considered all of these pros and cons and more, and for the purpose of this talk, we've decided to go ahead with a vision solution in the cloud. So what are the design principles that we consider here? Whoa. Sorry. We're going to talk about modularity, inter-process communication, and scalability. So let's dive right in. And I love this GIF because it shows exactly what we're trying to achieve here. Let's take an example. Let's say your product manager comes to you and say, hey, can we identify red Ford Mustangs in images? I'm a computer vision scientist. I say, why not? Collect me some data, label it as red Ford Mustangs, not red Ford Mustangs. I throw it at a classifier that I think works best, and voila, I have something that gives me precision recall numbers that work well, and my job here is done. Not so fast. Let's say this product manager comes back to you and says, hey, that campaign ran really well. Can we now identify blue BMW C4s? And hopefully, we already know where this is going. So at GumGum, a lot of the times, the kind of requests that we as CV scientists get are very much like this, where the base task is somewhat the same, but it has minor changes that could potentially lead to us having to retrain the whole model or set up an entire different infrastructure. So in an effort to reduce this work on us for the future, we came up with what we call as computer vision modules. Now, this is nothing new. You can consider computer vision modules as a black box that does computer vision work, that has an input as an image and outputs a bunch of labels. Now, this black box that does computer vision work could be either machine learning based, could be feature matching, a hybrid of these, or just simple design logic. The way it works here is that we take one or more of these, and each of them are housed in their own Docker images. These images will exist in their respective autoscaling groups, and each of these autoscaling groups will be associated with their respective queues or load balancers. This unit of a queue and an autoscaling group is what we refer to as a computer vision module. Now, taking this concept, can we solve the previous problem of identifying blue BMW Z4s in a more efficient way? Why not? Let's say you had an object detector that had vehicles as one of its classes. It sent its result to a make and model classifier, which then further sent its result to a dominant color classifier, that way giving us blue BMW Z4s. Another advantage of having these modules separated in this fashion is the ability to have one of them implemented in, say, TensorFlow, and so on and so forth. This gives your computer vision scientists the ability to work in an environment or in a framework that they're most comfortable with without having the time to production increased. Now, this sequence of modules is what we refer to as computer vision module pipelines. And these pipelines are only as efficient as they can communicate. We, like a lot of other applications out there, use JSON for inter-process communication, which takes me to my next design principle. So two of the most important features or characteristics of this JSON that we figured are important are structure and scalability to that structure. Now, in order to give you some context about why scalability, if you change your application from, say, a classification model to a detection architecture, and then for some other reason go ahead to a segmentation architecture, you, for as far as possible, don't want this JSON structure to change. So keeping all of that in mind, the structure that we came up with was that of a region and a property. A region is essentially a list of points describing a contour, and each region is associated with its own property. Now, a region can also be associated with multiple properties, thus solving the problem of red Ford Mustangs. So when you talk about scalability with this structure, you could now have the region be just the 4 coordinate endpoints of your image for a classification or an image level solution. It would be 4 points of the bounding box for detection, and it could be a list of endpoints for segmentation architectures. We also have the concept of a subregion. Subregions have all the properties of regions, along with something called as a relationship, which helps define relationships between multiple regions. So now when we look at the structure of your JSON, we know that it works really well for at prediction time. You have an image, you send it through your pipeline, and you have a JSON that works well. But what about the structure of this JSON when it comes to the entire life cycle of developing, continuously improving computer vision modules? So Greg is going to talk about that, and I hand it over to him.
Thank you. Hello? Can you guys hear me? Cool. Yeah, so Nishita just described the way that we structure our data and how the data that communicates between processes. And I'll discuss why that is beneficial in the life cycle of a machine learning model. So where's the pointer? There. So in a traditional supervised machine learning model that we want to deploy into production, we gather some data, for example, cars on the road. We have someone annotate them, bounding boxes or segmentation masks. Then we send that to be trained with whatever model we want to. Once it meets a certain accuracy that we're happy with, we put it into production. We serve it in traffic. And not shown here is we should have some kind of monitoring system. So we can gather maybe the low-performing classes or the low confidence detections and feed that back into data collection, annotation, and verification. And now we have the poor performing classes of the model re-annotated, and we send that back to be retrained and put it in production again. So this cycle is really important for scaling up the performance and the class support of your machine learning models. And having a data model, a data structure that is common to both prediction serving and training data makes this whole cycle amenable to automation. So we can have this continuously training over and over. Yeah, we get good models that way. So another detail that I'm going to talk about is data serialization. We could just send it as JSON, but there are pros and cons to serializing the data. So there are some of the popular libraries for data serialization is Avro, Protobuf, Thrift. So some of the pros is that there's a safe contract between producers and consumers. When a consumer, for example, receives a message, it knows for sure what the structure of the data is that it's receiving. Another pro is up to potentially 10x reduced file size. So if storage costs are important to you or efficiency of the transfer time. We sometimes deal with videos that are 4-hour-long sports broadcasts, and we keep all the information in one file, so the 10x reduced file size is quite important. Cleaner data. So say we had just a bunch of data in a lake somewhere. We know for sure what the structure of that data is inside. And schema evolution. With these libraries, say we wanted to add a new field to the schema that we didn't have before. There's a well-known process to change from the old schema to the new schema, as well as migrate all your old data to the new format of the data. Some of the cons is that this kind of data schema changes requires careful effort. If you mess up, sometimes you'll find files where you don't know how to deserialize or whatever. Some other cons is that there's overhead for this. You have to maintain the code for serialization. You also might want to maintain a registry, which is a separate server which contains, this schema with this ID was at this date, and previous schemas were, et cetera, et cetera. Okay, so the next design principle that I'm going to talk about is scalability. In particular, horizontal scaling. So when I say horizontal scaling, I mean we have a high amount of requests. We want to increase the number of workers or increase the number of instances, as opposed to vertical scaling, which is increasing the compute power of the box. So as we talk about scalability, just want to think about this data flow diagram. So we always have some in either an synchronous or an asynchronous application. We have a client or a producer of requests, and we have a server or a consumer of requests. And in the middle is this buffer guy. It could be a message queue or a load balancer. And these are some scaling triggers that we can think about as the traffic increases or decreases. So the simplest is just the number of messages in that buffer. For example, we use Amazon's SQS, simple queue service, combined, actually we don't use this anymore, but you can combine SQS with CloudWatch alarms, which is just a monitoring system saying, okay, we've received this many messages in the queue, now we want to scale up to this number of instances. You can also use ALB, which is the application load balancer for AWS. A more granular scaling trigger is the number of messages combined with the average CPU utilization in your fleet. So you can use custom logic in a Lambda function, which is just AWS's serverless compute platform, to measure the CPU utilization across your fleet. And some other approaches are container management solutions like Kubernetes, Elastic Container Service. So putting it all together, how we do it specifically at GumGum. This is just kind of a high-level data flow for one application. So say, for example, we have our ad serving platform send us a URL of an image, and they want to know what's in it. So they'll send a request to this controller API, which is just the front end that routes the request to the right AI application. So it'll put the request into a queue, and then we have one AI application that pulls that request from the queue. This AI application is contained in a single Docker. And the reason why I call it AI is because we also have an NLP team at GumGum. So it's agnostic to that. So once it receives the request, downloads the media, processes whatever it finds, puts it into that structured response JSON that we have been discussing, serializes it and sends it back to the controller, which returns it to the client. And bringing in auto-scaling that I've been discussing. So based on the number of messages in this queue, we can scale up this auto-scaling group, just increase the number of Docker images. I'm going to go even more into detail to describe what goes on inside one of these AI applications. And we built this framework, which is around a single application called multivitamin. It's a Python framework for serving machine learning models. It's agnostic to any framework, so you can use TensorFlow, PyTorch, whatever you want. It's on GitHub. It's pretty rough. We just recently opened it up, but try it out. Let us know what you think. So the data flow within one application is we have these selection of APIs. For example, one could be an SQS API, which pulls from the queue a JSON request. It packages the request and then sends it through a list of modules, these CV modules. It could be a vehicle detector combined with a make model classifier. And then we populate that response, serialize it, and send it to, we have also a selection of APIs to send the response to. It could be in S3 somewhere. It also could be a HTTP post to a certain endpoint. And now I'm going to go over a brief code sample of an actual piece of code that's in production at GumGum. And it's for, Nishita mentioned the GumGum sports product. So in the NHL, we want to know where a specific logo shows up, for example, Geico, and it shows up along the static dashboards of the rink. Right? So we'll instantiate two models, an NHL placement detector, which placement is just describing the location, which is an object detector, and then a logo classifier. And because we've designed modularity into it, these are separate. And when we construct this server, they can just be linked together in a list. And also because of the data structure that we enforced, we can just pass them one to the other. And then we define which input to pull the requests from, SQS, and then which outputs to write the responses to. It could be S3 or some HTTP endpoint. And we start the server. And then here is an example of the output of our detector. So you can see in-ice logo, which is the placement, and then below it is the sponsor, Toyota, along with the confidence. And you can see all the ones along the dasher board. I'll hand it back to Nishita.
So to wrap it up, here are a few of the things that we'd like you to take back with you. Before you start designing a computer vision solution in the cloud, I think the most important thing that will drive your design would be client requirements, because that not only defines the precision recall numbers that you need to hit, but it will also dictate your scaling policies, if you have a service level agreement or not. Scalability in terms of being able to serve different client requests quickly and efficiently will lead you to modularity. Modularity helps you build complicated computer vision module pipelines. But these pipelines are, again, only as efficient as they can communicate, as well as they can communicate. And so inter-process communication is important. And not just when it comes to prediction or serving time, but also in the entire life cycle of your of developing computer vision modules and improving them over time. And a key feature that ties all of this back together is efficiency, not only in terms of developing things quickly and running them smoothly, but also efficiency in terms of utilizing your instances correctly so that you save costs and eventually time. And with that, we'd like to open up for questions. Thank you.
Howdy.
I have a question about, so when you wrote your applications, did you use any of the, let's say, open platforms like OpenCV or did you consider them, essentially, or OpenVX, that kind of stuff?
So one thing that was important, so we do use OpenCV for certain features, like media retrieval. There's just some good functionality there. But we did want to, one principle we wanted to keep available is for us to use any deep learning or machine learning framework we wanted to. So we didn't want to have that be a requirement for everyone. So, no. Yeah.
But OpenCV kind of supports most of the...
Yeah, it does have a lot of functionality. So yes, we use some of it, and yeah.
Just to add to that, like what he's saying is that we use OpenCV in the multivitamin part of it, which is more like does the serving of your AI applications, but it's not a requirement that your AI apps must use OpenCV. You're free to choose whatever framework that you can use to, that you'd like to use to implement all of that.
Any more questions? I have a question then. I have a question for you. So, first of all, I want to thank you for the great presentation. It has great process related. So, but the one I'm seeing is that because this is not completely related to the cloud, right? Because, you know, if you go back to the first example you gave of a TV with advertisements, and then it is context-based advertisements. What if you have an intelligence built into the media player at the edge itself? So can you build your solution there on the edge if you have a right platform?
Do you want to take that? Okay. So that is definitely one of the applications that we are looking into. Initially, the way GumGum started and the way it implemented its technology, we're like the middlemen between the brands and the publishers. So if we had to serve a whole variety of publishers, we would have to make at the edge. We would have to make sure that we are compatible with a never-ending list of edge devices. So that was not the first goal of having in-image ads served. So the cloud was the best way to extract the kind of media that we'd like to analyze and then serve. But yes, there are a lot of applications where we would benefit from directly interacting with the edge. And those aren't straightforward solutions for us because it's something new and we don't have like a hardware team yet. Mm-hmm. But keeping that in mind, like we definitely like looking into having solutions for that as well.
Thank you. But if you have a common framework, say for example, at the edge, if you have a common framework, and if you take the load out from you on the hardware part, and then have a common middleware, say for example, so will your models, your products can actually run on that?
Yeah, for sure. If it was common, it would be a lot easier.
We're working on an application that is going to have many thousands of endpoints out there in large bricks and mortar facilities, and they're going to be doing biometrics. So we're planning to just capture the face, the wanted poster, we'll call it, of the person, and then ship that on up to a cloud recognition software like Amazon's or other vendors. Is there any recommendations you have on? We want to limit the traffic. We don't want to send us, live video from thousands and thousands of endpoints real time up there. So we want to limit the amount of flow. Is there any lessons you can pass to us about how do we limit the traffic so we're not hitting the head end with all this raw video?
Is your issue particularly with video then? Good. Because one thing you could think about is just sampling the video at a very low frame rate. Just take one frame every few seconds or something.
Yeah, we're planning to maintain session of, say, a face. We know it's there, but let's say you turn sideways. We don't have this biometric anymore, but we have the face. We know that's the same human. So we'll limit that amount. We won't resend that poster because that's not a good face to send up. This is a good face. So we're doing pose estimation. So we're trying to limit the amount of pictures being sent up to re-verify who it is.
I see.
But then later we may want to do other features.
Yeah.
Like a hand gesture or something else. So architecture, this type of scalable platform that we can drop in new neural networks to support all these things is going to be.
Yeah, and if you have, if you keep in mind different modules, you could have one module that kind of filters out the traffic. So say, if there's no face, don't send it to the next thing to be processed.
And you would suggest doing that on the edge, as much as possible on the edge, that filtering?
You could. I guess face detection on the edge is pretty well defined. So.
Yeah, we kind of had a similar situation with the sports project where essentially when you have large 4-hour-long videos, you don't really want to process every frame, but you want to make sure that you're processing frames that have logos and placements that you care about. And so we would have you'd set up your pipeline in a way that your first layer is just doing filtering. So it downsamples your video, and then you do some kind of generic filtering where, say you have a classifier that says, do you see the quote or not? And then you only take those images and then pass them forward, so that if they're shots of the audience, you don't really care as much obviously, all these rules will depend on what your requirements are.
Another example is that we analyze all social media, so we get millions of posts coming in, and we can filter out, like, if it's not sport related or something, don't analyze it anymore. Yeah. Cool. Thank you.
Thank you.
Thank you.
Big round of applause.